In regression, what are we trying to predict? Okay, to just to help you understand, let me give you an example. Let's say I have a feature called let's say income. Okay, let's say annual income, and I have a feature, not a feature, a variable called expenditure. Again, annual. So can anyone tell me what we are trying to? So if this is my x and this is my y, what are we actually trying to predict? Any guess? Any guess? Because we typically, you must have seen, we write it as y equals uh, some w transpose x, or in this case there is only one w, so wx plus some bias plus some error, right?
In this, we are trying to predict W at ML.
Ah, okay, okay, okay. I'll make that clear. Uh, so to predict is different, and to estimate is different. Okay, we are trying to estimate w using w hat ml or w hat ols, whatever. To predict means we predict a variable, predict unseen values of a variable. So prediction means there is a variable that you're interested in. Let's say in this case it is annual expenditure, and we're trying to predict unseen values of the variable, or you can say using unseen or using new values of the income, you're predicting the corresponding expenditure, right? Actually, the point I want to mention here is that let's say there is someone, there are two people, let's say both of them have the same income, but they have different annual expenditure. Is it possible?
Yes.
It is also possible that if you look at the entire country, there'll be so many people who have the same annual income but different annual expenditure. That is also possible, right? So if I plot this, it will look something like this, right? Because there could be several data points which lie vertically. Okay. So now let me ask this question again. What are we trying to predict? If there are so many uh, correct values corresponding to one value of x, let's say this is x1. Okay. So even corresponding to x1, there are so many values of y1, right? So what are we trying to predict? Is my question clear?
So can
Yes,
you
the
please repeat?
question is clear.
Mhm. Because I mean, I don't know if you have seen these kind of examples, but if not,
Yes,
then
sir,
this is a
I'm
time. Okay,
trying to understand. So basically, we are finding relationship between annual expenditure and income.
correct.
Some kind of
And
relationship is there.
yes, that is true. Uh, and why are we trying to find that relationship? Because we want to predict values of the expenditure if somebody gives us values of income, right?
Income. Yeah.
So, but if there are many correct values, right, then isn't it possible that at some x2 where you know the income but you don't know the expenditure, here also there will be many correct values. So which one of these correct values uh, will you consider uh, as the correct value, well, when testing? Because when testing you have to do this y hat minus y uh, whole square and mean squared error and all, right? So which one of these will be the correct value? Essentially the question is, what are we trying to predict? Okay, so I'll not uh, play KBC anymore. uh, the idea is that we are actually trying to estimate not y but the expectation of y given x. This is what we are actually trying to predict. Okay, but usually people don't write this, right? Uh, so it remains kind of hidden. But yeah, this is precisely what we're trying to predict. What so if you think about it, in this case of in this example, then we are actually trying to predict the mean of these guys, y given x ka expectation. You can think of it as mean of these guys. And in x2, when you compute the test error, you're comparing it with the mean of these guys. Okay. Okay, so let me introduce this idea of expected label. So what I call as expected label or expected target is this guy, expectation of uh, okay, let me write it more precisely, expectation of y given x of y. Okay, and if you think about it, it is same as uh, you integrate over all possible values of y where your probability distribution is that of y given x, right? And then you do something like dy, right? Because the randomness is coming from y, right? As you can see, the randomness is over y because these points are distributed over y. X is fixed, x is given, and uh, and we're trying to estimate y. Okay, so this is given x, by the way, given some x in RT. Okay, so this is what I want to predict, by the way. Okay, just making it slightly more clear. Okay, what else do we have? What about, so let's say we have some data set. Let me call the data set D. Okay, so D will have a lot of inputs like this: x I, y I running from 1 to n. This is my D. Okay, and what do? We try to learn a uh, learn a model, right? Which depends on D, and it also depends on some algorithm, right? So let me say that, so there is a data set D. There is an algorithm A. So this algorithm can be anything. It can be MLE, it can be OLS, it can be MLE. Uh, in general, it can be any other uh, regression algorithm. It can be XGBoost regression trees, or it could be random forest regressor. Any hypothetical algorithm that you can think of. Okay, that is my algorithm A. Okay. And using this algorithm on the dataset D, we try to learn a model, right? So let me denote it as HD or FD as equal to A on D. What does this mean? This means we are learning the model FD using algorithm A on data D. Remember, this is my training data, by the way. Okay. This is not my test data. This is my training data. Okay. And what is my test error? So let's say we trained our model on this data set using algorithm A on dataset D, and we obtained this FD. Okay. Remember, FD will change every time you change the dataset, right? Which is actually true, right? Because if you change the dataset, you might end up getting a different model, right? And now the assumption is that, see, what is the most critical assumption of in the entire framework of machine learning is that this uh, test data set has the same distribution as that of training data set, right? That is the I don't know if it is explicitly stated or not, but this is the most important assumption in the entire machine learning framework, because if this doesn't hold, then there is no point of learning all these models, right? So the most critical assumption of machine learning is that the test data and the training data have the same distribution, right? Test and same distribution. Okay. And what is my test error in? So let's say I want to uh, or this is also known as the generalization error, right? Where you look at the expectation of uh, the predictions minus the actual points, right? But what are those predictions? The predictions we are doing using FD, the model which we learned, right? So you can say FD of x, okay, minus y ka whole square. And this expectation is over all these pairs xy which are coming from some distribution p, okay, and this p is the distribution that I mentioned. So train data and test data have the same distribution, call it p. And what is this red guy which I have written? This is the generalization error or test error, or more appropriately, it's the expected test error, right? Expected test error. Okay, this part is clear, right? Why is this the expected test error? I mean, I'm just taking expectation instead of averaging, right? Because here I'm looking at it from a probabilistic point of view. Okay.
Yes, sir.
Now I can write this as uh, some sort of an integral, right? Integral over x and integral over y, right? And this term can be written as f dx minus y ka whole square, okay? And then probability of the joint probability of x and y with dy and dx. Okay, this is fine.
Yes, sir.
Cool. And this is my generalization error or expected test error given my given fd, right? This is important. Given fd, this is my generalization error, because we are assuming that hey, I have trained the model. Now I have one trained the model on the data set using some algorithm, and I have these weights or the model fd. Now I want to check the generalization error or the generalization capabilities of fd. Okay, that is what this does, right? Now observe one more thing. Okay, one more thing that, okay, before this, okay, let me, so these fds that you obtain, now I'm going to randomize that also. So there are so many FDs that you can obtain, right?
Yes, sir.
You can
Basically, it
obtain,
depends on the training data, right?
correct. It depends on the training data, and the training data in itself. So the training data in itself is coming from this hypothetical distribution P or Pn. Why I'm writing Pn is because here I am assuming. So if here I assume that x comma y comes from P, uh, and the training data has got n n data points, so I can say that the D is drawn from, or D is a D is sampled from P power n, right? Because there are n of them, right? And because of this, I can define this very important entity, expectation of D coming from Pn Fd, right? So what is this guy? This guy is the expected model, or you can think about this as, if you vary the data sets, right? Still, you will end up getting a. So you can think about this as the average over the functions that you will obtain by training it on different data sets. This is a very hypothetical quantity, by the way. So let me call this f bar. And if I want to express it in probabilistic terms, what do? I integrate over the data set, right? Over multiple data sets, and then fd, and then what is the probability of let's say obtaining d, and dt, right? Something like this. I'm just writing it vaguely, but yeah, this is fine. Okay.
Excuse me, sir.
Go ahead.
Sir, I actually have a basic doubt in above equation.
Huh.
Okay, so here we are calculating the expectation of test error, right? So
Yeah.
generally we are like the actual value of error into the probability of getting the error. So here we wrote like probability of getting the data. So I'm not getting this term.
See, whenever we take expectation over something, so in this expectation form, what is the random component? X and Y are random,
X
right?
and Y, yeah.
Huh. So we always multiply by the probability, or you can, I mean, you shouldn't think of this as the probability. This is actually the probability distribution. Okay. So this need
But it's
not.
distribution of data, right? Not the
Yes,
error.
distribution of data, not the errors.
Yeah.
Distribution, what you so okay, that is another point. That in some models, in fact, in regression models, you assume that uh, the error has a distribution. Okay, that is a different idea. This is more general. This is holding for any model that you will define in the future.
So then we have to,
So
going forward the.
whatever you mentioned, can you tell me? I will write it down. Like what error what error formula you're referring to?
No, I'm not referring to it, just a doubt.
Oh, I see.
The
Okay.
expectation is we calculating the expectation like, actual value against the probability. So if we are calculating the test error expectation, then it should be like value of error into the probability of that error over
Okay.
the data. That's my question. Yeah.
Okay. Okay. Got it. I understood. I understood. So let us say, let me draw this here. Let us say I have a random variable x. Okay. X is my random variable, which is, let's say, binomial. Binomial with n NPS parameters. Okay. So in this case, what is the expectation of x square? I will write this as x square times probability capital X equal to little x, right? What is
Yes,
the
sir.
expectation of, let's say, log x summation log x probability x equal to capital X, right? So in all cases, you're looking at the probability or the PMF of the data only, not of the function. In this example, this is my function and my randomness is over this data distribution. That is why we are taking the probability of the data distribution. We always do that only, right? Because whenever we want to take expectation of a function of a random variable, right, we don't take probability of that function. We take probability of the random variable only, and the function comes in front of it. Is it clear?
Oh, yes, sir. Clear now. Yeah,
Okay,
got it. Thank you, sir.
okay, no worries. Okay, so that is my generalization error, and this is my the second thing I wrote is my uh, what is this called? This is the you can think about this as the expected uh, hypothesis, or okay, the word hypothesis is slightly, I think, confusing, but uh, you can think about this as the expected regressor. Okay, because we are using a regression problem, so you can think about this as expected regressor or regression function. So here we are varying the data set itself. Now what I'm trying to do is uh, I have a generalization error. I wrote a generalization error where I have fixed FD, which means I have also fixed D. Now I'm going to vary D also. Let's see what we get. So now I'm going to vary D also. So I'll write the same, uh, you know, formula. XY is drawn from P and D is drawn from P power N. So I'm varying the data set also. And then I want to compute this entity FDX minus Y ka whole square. Here observe X is random, Y is random, the choice of D is also random. So this can be thought of as, there are three integrals D, X and Y, and then you have FDX minus Y whole square. Again, now you can question also that why am I taking this square, right? Why am I not taking mod, or why am I not taking log? There are so many questions that might arise, right? But there are different variants to it. We are taking square as of now because that is very easy to work with. That's all. Okay. In general, you can take any loss, any kind of a loss, right? Which makes sense, not a random loss, but yeah. And then I multiply it with the probability or the probability distribution of x and y along with the probability distribution of the data set D, right? And then I have to do dy, dx, and d capital D. Just notational, don't worry.
Sir, can you please explain it again? Just
This part?
what is it? Yes, sir.
Okay.
Just give a
So
bit.
here what I'm trying to do, it is same as the expected test error with D being random. So I'm changing my D also. You can see that there is an additional uh, PDF here, right? PD is additional and DD is additional, right? And here there is an integral which is additional integral D. So what I'm trying to do is that instead of uh, seeing, okay, I took a training data set, I trained a model, instead of seeing how well that model performs, here I'm trying to see, okay, if I hypothesize that FD is, let's say, linear or has this form and all, and if I uh, produce multiple such models using different training data sets, what can I say about the expected test error? I'll give you a better perspective of this. Okay, just a sec. So in the earlier generalization error, what are we trying to see? We're trying to see how good is our trained model FD. This is what we are trying to see, right?
Yes,
And
sir.
how is FD obtained? FD is obtained by using the algorithm A on the dataset D. I've written it here.
Yes, sir.
Now I am saying how good is my uh, hypothesis on FD, which means that even if I change my training data sets, right, how good will be my model? Okay, so let me write it here.
Got
So
it. Got it.
how good is my uh, assumption of FD, uh, even if I train it on different data sets? Okay, cool. Hmm. Okay, so we looked at two generalization errors. One is given FT, and this is given. You can think about it as given A. Okay, so this is given A because only A is specified, and FD is obtained every time by changing the training data, right? So this measures how good is my algorithm in some sense. Okay, algorithm. All right. Okay. So what did we do? We started with uh, the expected label. We said that we'll train on the training dataset using an algorithm A, and we'll obtain a model. How to test how good a model is? By using this form of expected test error. And then we also observed that D in itself, the training data in itself, could be random. So you can think about an entity called expected regression function, and you can use that randomness of D, which is the training data, and say that you can test or you can see how good your algorithm is irrespective of the training data, right? That is what we did. Now let me further extend it and say that Just a second. Manipulator. Okay. Okay. So what is our point of interest? My point of interest is expectation of fd of x minus y ka whole square, right? Where what is random? X is random, y is random, d is also random. Okay. Now I can write this as expectation of f dx minus f bar or f bar x plus f bar x minus y iska whole square. I just added and subtracted f bar x. Remember what is f bar x? It is the expected regression function. Okay. And here also the expectation is over x, y, and d. Now what I will do, let me break it down. I'm sure everybody is aware of this kind of breakdown. Yeah, so f bar or not f bar, it's actually f dx minus f bar x का whole square, ठीक है, plus expectation of f bar x minus y का whole square, okay, plus 2 times expectation of uh, f dx minus f bar x multiplied with f bar x minus y, right? This is what we have, right? I just expanded the square, by the way. Okay. Observe that in the first component there is no y, right? So this is expectation over x and d only. In the second case, it is expectation over x and y. And in the third case, the expectation is over x, y, and d. So when I say expectation is over something, that means that those things are random. In the first case, x is random and the training data set is random. In the second case, x and y are random. And in the third case, x, y, and d are random. But what can you say about this third guy? This third guy is very notorious, by the way. This guy is very notorious. Can anyone tell me what this will be? Any guess? Any guess, guys? I mean, you must have done something similar, right? And in those cases, what does this guy turns out to be? Okay, we will see that it is zero. Okay, but I will explain it. So observe that the expectation over D is only, so D is only in the first component, right? D is not there in the second component. Right? So I can push the expectation of D inside this, right? So I can write it as expectation x and y over x and y, right? And then I'll push the expectation of D inside this and say that this is f dx minus f bar x and then multiplied by f bar x minus y. Okay. Okay. But what is this guy? This guy is nothing but, see, what is expectation over the data set of f dx? That is nothing but f bar x, right? So this guy is f bar x minus f bar x. And because of this, the whole term is equal to 0. So what does this, so okay, first of all, what is this that we started with? We started with the expected test error, right? So let me write it down.
Excuse me, sir. Could you please repeat it? Why it's getting zero?
Okay, sure. So, uh, did you understand the fact why I pushed in the expectation? I pushed in the expectation over D because D is only present in the first component, right? So there are two components, fdx minus f bar x and f bar x minus y. D is only there in fdx minus f bar x, so I pushed in expectation D, right? Now I used this fact. Where is it? Huh. See, expectation over fd is nothing but f bar. That is how we have defined f bar, right? Because of that, this small guy turns out to be expectation of fd x minus f bar x, and that is equal to f bar x minus f bar x. F bar x minus f bar x is 0, and so this entire term becomes expectation over x and y, uh, f bar x minus f bar x times f bar x minus y, and this term is 0, right? So this entire term is 0. Is it clear?
Yeah, sir, it's due to the assumption, right?
Not
That
assumption, that how that is.
expected value of.
It is not an assumption, it is the definition of f bar. That is how we have
Okay,
defined f bar. So
okay.
f bar, so you can think about this as, this is the person and f bar is the name that we are giving to that person. Okay.
Yes, yes, sir. Okay.
So we started with the expected test error, and what did we see? That the expected test error is nothing but, there are two important terms. The third term is 0. There are two important terms. This term, number 1, and this term, number 2, right? Okay. Anyway, I had some other plans in mind, but since we have started and we are neck deep into this, let's finish this. Okay. Okay. What is this first entity? Anyone, any guess? Can anyone take a guess on what is this first entity? Okay. So the first entity says, so the first entity is nothing but, uh, let me use green. You can think about this. See, just observe that this is same as expectation over x comma d. Okay. F dx minus, what is f bar x? It is nothing but expectation of f dx, right? Iska whole square. Now, what is this? This is something everybody is familiar with. This is the variance, right? Isn't this the variance of f dx? So, what does this capture? This captures that even if I take a lot of different training data, right? How far will it be? Or you can think about this as, uh, what is the impact of the data, right, on my model, and the impact is measured by how far it is moving from its expected value. Okay. So the variance, so let me make it more clear maybe. So let us say this, we have a space of all uh, models that you can obtain using these data sets, right? So let's say in one case you have, okay, by the way, these are not, this is not R2. Okay, this is just a hypothetical space of all models that you can obtain using different data sets. So using one data set you obtain some model which is here, using other model you obtain some model, using other data set you obtain some other model here, and then these are different models that you're obtaining, right? and the mean of all of these guys is, let's say, somewhere here, right? And that is, let's say, your model. You specified an algorithm, okay, or let's say I specified an algorithm, let's say A1, and I got this. This is my generalized. So the variance of, uh, so this entity which I wrote, part one, okay. And let's say someone else out of you guys specified another algorithm, A2, right? And there, if I change the data sets, I'm getting these models where the mean is somewhere here. Which algorithm is better? Hello?
A2.
Yes. Why A2?
So because in A2 we can get the less errors as compared to A1. So
Yes,
that's
that is exactly what part one signifies. What, so you can think about this as the variance of the models that you get when you train on different data sets. Is the idea clear, everyone?
Yes, sir.
Okay, I don't think this any of this is in the syllabus, but yeah, I mean, anyway, covering all this because I started with this. Okay, that's why I'm covering it. Uh, as I mentioned, I had some other. We can have some extra tier sessions also if you want to really complete the syllabus and do all that kind of shit. But yeah, let me complete this as of now. Hmm. Okay, so we have an interpretation for part one, but what about part two? Part two says expectation of x and y, f bar x minus y whole square, right? What we will do, we will break this down further. Okay, let me use red. If you look at part two, what is my part two? Expectation of, there is an x, there is a y, and there is a d. Right? F dx minus y ka whole square. Right? Now what I will do, I will let me think of, yeah, okay. So what I can do is I'll use a kind of a similar trick. I'll multiply by f bar of x. Sorry. Yeah, I'll multiply by, sorry, not multiply. I'll subtract f bar of x and then add f bar of x. Okay. Plus f bar of x minus y iska whole square, right? And wait, just a second. The second term was expectation over x and y only, yeah, because there is no d.
Yes, sir.
There is,
Please.
yeah, there is. What? Oh, I think I wrote the wrong term. Just a second. F bar x minus y, है ना? F bar x minus yx. Uh, let me call it y only. It's not yx. It's just y because the true label. F bar x minus y whole square, and then I can write this as f bar x minus minus what? Minus. Let me take y bar x. So I have to explain what is y bar x also. Okay, I'll explain anyway. Y bar x plus y bar x minus y. Okay. So what is a y bar x? Let me now go back. Let's go back to where we started all this from. We started all this from saying that, hey, uh, what we are estimating is not y but expectation of y given x, and this is what I'll call to be y bar of x. Okay. So that is what I'm subtracting and adding. Now this, why is this useful? Because now I can write this as expectation of uh, f bar x minus y bar x ka whole square plus expectation of y bar x minus y ka whole square, right? Plus again expect two times expectation of uh, f bar x minus y bar x multiplied with y bar x minus y. Because of some uh, good things human beings have done in the past, it turns out that this term is also zero. Okay, why is it zero? Because so see what is the expectation over? It's the expectation over x and y, right? Right. Now what I will do is mm, so you can see that the expectation over x and y, this can be written as expectation over x and then do expectation over y given x, right? I mean, this is same as saying that probability of x comma y is same as probability of x into probability of y given x. Okay, right. This is okay.
Yes, sir.
Okay, so we will use this, and what we will do is that we will write expect this whole expectation or this whole term as expectation of पहले y given x का करूंगा, उसके बाद expectation over x करूंगा of this entire term f bar x minus y bar x multiplied with y bar x minus y. ठीक है. Okay. Let me push this inside. इसको अगर अंदर लेके जाता हूँ तो ये हो जाएगा 1 Okay, cool. Okay, so what I can do is okay, so I can take okay, let me write it once again. Expectation over x, and then there is one term which is f bar x minus y bar x times expectation of y given x of y bar x minus y. What did I do? I applied the expectation of y given x only to this second component. Can anyone tell me why? Because in this first component, y is not random, right? And whenever you say y given x, then it means the randomness is over y and x is given, right? Here y is not random in the first term, in this term which where I have not taken expectation of y given x, right? But in the second case, y is random. This is the randomness in y. See, y bar x is in itself expectation of y given x of y, right? So that it doesn't have the y component in it. Whenever you take expectation of a random variable, that randomness of that component gets, it is done away with. It's gone. Okay. So the first component doesn't have it, only the second component has it. But what is the second component, by the way? The second component is nothing but y bar x minus expectation of y given x of y. Now that is same as 0, right? I mean, that is how we define y bar. So this is how the third term also vanishes. Okay. What is this first term, by the way? So we have, okay, we have two more terms. So let me call it the third term, and this is my fourth term. What does the third term signify? Okay, first of all, the third term has only x. There is no y, there is no d. See, remember, y bar, we have taken expectation over y, and we have gotten rid of the randomness in y. So in y bar x there is no y, but here there is y. So this is x comma y, right? Right. What is this third and fourth term? So third term. So third term says that, let me go back to the initial diagram. Let us say my actual average of x2. Remember, we said that x2 is something unknown to the training data set. So the actual average of x2 is somewhere here, right? Of x2, or you can think of this as y bar of x2, right? And let us say I train a lot of models. Okay, how do I train them? I use different data sets, but the same algorithm. Remember, it's the same algorithm. Okay, in the same algorithm, I train across different data sets, and I get different models, and then I take some average of it, right? And then I get this. That is what I call to be f bar of x2, right? Now this gap, right? In fact, the square of this gap, that is what we have here in the third term. And this term is known as the bias, or the bias squared. Okay, so this, what does this capture? This captures that, hey, even if you have an option to train across multiple data sets, multiple training data set, still, how good can your algorithm be? Okay, so so again, let me you know uh, let me give a diagram. So let's say I have a class of models. Okay, this is a1, which I have proposed, and someone else proposes some a2, right? And this is my, let's say, uh, or let me think about it different way. Mm. See, the bias has an expectation over x, right? So what it is saying is that when you take average over x, right, of this distance, right, uh, the distance between f bar x and y bar x, right, then, okay, so let me write it like this. See, yeah, the problem is I don't want to use this kind of a diagram because I use something similar, and if someone is looking at the notes and all, they might get slightly confused. But okay, anyway, okay, let me use some other color or something like that. Let us say for a given x, okay, or you can say for okay. So suppose I have points like this. So what are these points? These points are true data points, right? True data points corresponding to different values of x. Okay, not true data points. True, you can say y bars. So what is y bars? Uh, Expectation of y given x, right? So each corresponds to some value of x. Okay, okay, and then you make these predictions, and then you get f bar x, right? And you observe that the f bar x that you get are something like this, or yeah, let me make it more clear. These are the f bar x's that you get. Okay, and in the other case, you have in A2, you have something like this, where these are my predictions, and let's say these are my labels. Okay, so can anyone tell me which algorithm is better again?
A2.
A2 is better, right? Because the bias is less, right? Okay, so that is the bias component. Okay, okay, what we have done is we have formally, rigorously, without any doubts or without any imprecision in terminology, we have derived something known as the bias variance trade-off. Okay, what did we start with? We started with the expected test error, and we broke down into different components. There was a bias term, there is a variance term, then there is an additional term which I haven't talked about yet. Can anyone tell me now, because you've been following it for a long time, by this pattern, can anyone tell me what is this uh, fourth term? Anyone? So the fourth term is random noise. Okay, why is it random noise? Because okay, what is the fourth term in the interpretation of in this example? In this example, this noise, okay, this entire, you know, uh, see, ideally, what we wanted it to be at a single point, right? But because of some noise, what is that noise? Nobody knows, because it could be different people have families of different size, right? Different people have different financial conditions, different people might have taken different loans. What is all of these factors? All of these factors or variables we have not taken into consideration. Okay, and this difference, this red difference that you see here, right? This is due to all the factors or variables that we have not considered yet, right? So let me write it down. The fourth term captures variation due to all variables that we have not considered. And this term is known as the noise. Okay. Okay. So let me write it once again. So we saw that this is known as the bias variance trade-off. And what did we see? We saw that the expectation over x, y, and d, f dx minus y whole square, is same as expectation over x and d, f dx minus f bar x whole square, plus expectation over x, f bar x minus y bar x whole square, okay, plus expectation over x and y bar x minus y whole square. This is the variance. This is the bias squared. This is the noise. This is the mean squared error or generalization error. Okay. Okay. Cool. Hmm. So now what we will do? Okay, this is all good. Uh, can anyone tell me what is the bias and variance for the linear regression case that you derived? Did anyone try it out or anything that sort? Anyone? Anyone? Is there anyone in the meet though? Let me see. Oh,
Yes, sir, but haven't
okay.
tried.
Okay, okay. So can you tell me what it turns out to be? Do you remember? So okay. So first of all, let me start with the basics. What does the model look like? It looks like y equals some beta. In fact, I should write it like this: y equals to x times beta, or is it x transpose beta? Depends on how you take your x. Yeah, x transpose beta. Okay. Plus some error epsilon. This is what? This is my linear model, right? Linear regression. So again, remember this y is actually not y. It's this actually expectation y given x. Okay, just for abuse of notation, everybody is using y. Okay. So okay. So in this case, what was my beta hat? OLS or beta hat MLE? This was something like XY, and then we had XX transpose ka whole inverse, है ना? If I'm not wrong.
Yes, sir.
Yeah.
Yes, sir.
Again, this is everybody can derive this, right? Using the classic. You take the derivative and set it to zero and all that. Everyone is aware of that, right?
Yes, sir.
Okay.
So what is
Yes.
OLS?
Oh, ordinary least squares.
Okay.
Okay, I'll explain. Just a sec. So, I mean, uh, so when you derived this, what did you do? You took y minus x transpose beta, iska norm square, right? And then you try to minimize this, right? And whatever you obtain by minimizing this, that is known as beta hat. Beta hat OLS. Okay, that is one framework. Here, there is no assumption about these errors. The second framework is where you assume that this epsilon, they are all normally distributed with 0 and sigma square I, right? And then you try to maximize the likelihood, and then you obtain something called beta hat MLE. Again, because of some good things that humans have done in the past, it turns out that Beta hat MLE and beta hat OLS are the same. For this case, for linear regression model, there are other models where it is not the same. Okay. Cool, cool. Okay. So, so what is the bias of these guys? So what is expectation of beta hat OLS or beta hat MLE? See, it is nothing but the expectation of. See, the randomness is only in epsilon, right? Nothing else is random. So whenever you take an expectation of something, just first you have to see where is the randomness. So here the randomness is an epsilon. So I write this as XX transpose whole inverse x times, instead of y I write x transpose beta plus epsilon. Right? What is this beta? What is the difference between this beta and beta hat? Beta is the true unknown parameter, and beta hat is our estimate for it. Right. So now this turns out to be what? This turns out to be, what does this turn out to be? This turns out to be XX transpose whole inverse XX transpose beta plus expectation of 0. Sorry, expectation of epsilon. Now this is 0 because epsilon we are assuming to be normal 0 sigma square, and this inverses will cancel out and we'll have beta. Right? I think. Okay. So what can I say about this estimator? I can say that this estimator is unbiased, right? I hope everybody knows unbiasedness. What about the variance though? So what I will do, let me denote the original uh, beta, right? Or you can say the true unknown beta as denoted by beta star. Okay. Otherwise, it gets slightly confusing. Okay, what can you say about the variance of? Okay, first of all, um, what can you say about test error to TK? What can you say about this guy? Expectation of mm, beta hat. I'm not writing MLE every time. Okay, beta hat minus beta star इसका norm square. What can you say about this? Has anyone tried to compute this by any chance? And if you remember, you can tell me what this looks like.
No, sir.
Okay, no worries. So this is same as expectation of beta hat minus beta star इसका transpose times beta hat minus beta star, right? Okay. Now, what is this equal to? This is equal to expectation of just a second. Just give me a minute. थोड़ा पानी पी के आता हूँ. Okay. Actually, it has some connection to the. So this is the mean squared error of the estimator, by the way. It has some connection to the generalization test error. Let me see if I get this done with, then we will discuss that. But yeah, okay. So what is beta hat minus beta star, by the way? See, from this equation, what we can know is that beta hat MLE or beta hat in general is equal to beta plus. Oh, what I didn't write here is these xx transpose whole inverse and then x. Okay, xx transpose whole inverse x times expectation of epsilon. Okay, and then the whole thing becomes 0. So beta hat is same as beta star plus xx transpose whole inverse x epsilon. Right? This will be useful for us. But using the yeah, so using this we can say that the difference between beta hat and beta star is xx transpose inverse x epsilon. So I can write this as xx transpose ka inverse x epsilon, and then this can be written as uska transpose, by the way, right? And then xx transpose inverse x epsilon. Right? Now I'll use something known as the trace trick. Okay. So just pay close attention. If I take two vectors v1 and v2, two vectors, let's say in Rd or Rn, right? What is the what is v1 transpose v2? It is a scalar, right? It's an element in R. So we can say that the trace of v1 transpose v2 is same as p1 transpose v2, right? And in general, for any matrix, in general, for any A, B, C matrices, the trace of A, B, C is same as the trace of B, C, A is same as trace of C, A, B. Okay. So using these two facts, there are two facts here. Okay, one is this fact and the other one is this fact. Using these two facts, I'll write this as the expectation of trace of xx transpose whole inverse x epsilon इसका transpose है ना, so इसका transpose and then xx transpose whole inverse x epsilon. Right? Now here what did I do? I used the first fact, and now I'll use the second fact, and I'll say that this is same as the expectation of trace of xx transpose का inverse x epsilon multiplied with Notice carefully, I'm taking the transpose of the other guy. So it will be epsilon transpose x transpose. Okay. And then transpose of inverse is same as inverse of transpose, right? So this would be xx transpose whole inverse, right? Now I will write this as so now the expectation is only valid for these two guys, right? Other two guys are deterministic. Only epsilon is random here. So I can write this as trace of xx transpose ka whole inverse, right? And then x, and then expectation of epsilon epsilon transpose, and then x transpose, and then xx transpose ka whole inverse. I know now it might look a little hectic, but it's actually very straightforward. Now you observe that epsilon ka variance is sigma square I, right? So this entity is sigma square into I, right? Now since it is sigma square into I can write the whole thing as, I'll take out the sigma square, right? And then there is an xx transpose here that will get cancelled with one of xx transpose inverse, and we'll be remaining with sigma square and then trace of xx transpose chi inverse. Is this fine? This is the variance, by the way. Since this is the mean squared error, right? In fact, this is also the variance because it is unbiased, right? So bias is zero. Variance and mean squared error are the same. Okay. Is this part clear that the mean squared error is this? Now I'll ask a very important question. In when you're doing this OLS or the MLE, you're taking inverse of XX transpose. What if it is not invertible? Anyone?
So basically, we were considering it as pseudo inverse.
Oh, I see. Okay, okay. Yeah, pseudo inverse will work. Yeah, yeah, pseudo inverse will work. Oh, I think. Okay, okay. Then it is fine. So, what is the pseudo inverse? Anyone? Sorry. Anyone? Can anyone tell me what is the pseudo inverse? What is the pseudo inverse? Hello.
Yes, sir, you are audible, but I don't know how to compute it.
Oh, I see.
Sir, pseudo inverse is like we adding
Hmm.
a feature, constant feature ones, right?
No, no, no,
To
nothing like
make
that.
it invertible. To make it invertible.
Uh, no, that is not pseudo inverse. That is the ridge regression.
It is reciprocal of
That is, so you're talking about adding, uh, you're talking about XX transpose plus lambda and then taking inverse, right? Is
Yes,
that what?
sir. Yes.
So that is ridge regression idea. That is not the idea of pseudo inverse. Pseudo inverse is, you can think about it as, actually, okay. So formal definition is that it should satisfy a few properties. Okay, so the first property is that x and then x ka pseudo inverse and then x again, that should give you x. The second condition is that x ka pseudo inverse x and then x ka pseudo inverse, this should give you x ka pseudo inverse. Uh, it should be symmetric. So x का pseudo inverse, no, not x का, x times x का pseudo inverse. इसका अगर आप ट्रांसपोज लेते हो, then you should get back x times x का pseudo inverse, right? And same with x का pseudo inverse times x. इसका आप ट्रांसपोज लेते हो, then it should be x का pseudo inverse x. Okay. So this is the idea of symmetry, and uh, this doesn't have a name, but yeah, you can see what it means. It's somewhat similar to defining inverses, right? But see, remember that I did not write the pseudo inverse. I wrote what is pseudo inverse, right? Why I did not write the? Because it's not unique. There can be a lot of pseudo inverses for a particular matrix. Okay, there is one way to compute pseudo inverses. Okay, the method is using SVD. Okay, using SVD you can compute the pseudo inverse. For example, uh, so how to compute pseudo inverse? One such pseudo inverse, but someone mentioned that pseudo inverse they have used to take you know to take this, right? Okay, anyway, that is
Yes,
fine.
sir. Yes, sir. I mentioned, but
Okay,
I haven't computed it in any numerical
okay, okay. No worries, no worries. So I hope you're aware about SVD, right? Singular value decomposition.
Yes, sir. In MLF, we study.
Okay. So if the SVD of x, okay, if the SVD of x is u sigma v transpose, okay, then x pseudo inverse, one such pseudo inverse, okay, because there can be several many. One such pseudo inverse is something like v, and then let me write something like, let me write sigma plus. Okay, I'll tell you what sigma plus is, and then u transpose. Okay, and what is the sigma plus? The sigma plus is this can be obtained by replacing, or let me just write it like this. So sigma plus is nothing but 1 by sigma. Okay, in fact, you if you remember, sigma will have only diagonal entries, right? What will sigma
Yes,
have?
sir.
It will have something like
Sigma.
sigma 1, sigma 2, and let's say sigma r, and then a lot of zeros, right?
Yes, sir.
This will be 0, this will be 0. And sigma plus is nothing but, you just invert the positive sigmas and zeros remain as 0. Actually, that's why I did not write 1 by sigma, because that doesn't make sense. It is actually 1 by sigma 1, 1 by sigma 2, 1 by sigma r, and then these are all zeros. All of them are zeros. This is my sigma plus. So this is a way to compute a pseudo inverse of x. Okay. Okay, this is for general x. Okay, for you have to compute pseudo inverse of that guy. X transpose x ka, sorry, x transpose x. That is uska pseudo inverse you have to compute. Right? Okay. Uh, by the way, I mean, can anyone tell me if? Okay, I think I have to cover. Let me cover ridge and lasso. Okay, quickly. There's only half an hour left. So, okay, one question that you can maybe think about later is that uh, I think maybe it's covered, but yeah, still, this guy. This is what, not x transpose x. X transpose beta equals xy, right? This is what you're solving for, right? To obtain beta. But does this always have a solution? Think about it. Okay, later on. So uh, okay, so this notion of regularization, I hope everybody knows. And so what is the notion of regularization? Anyone? See, the idea is that you don't want your weights to go out of control. You want to keep your weights in control. Okay. I mean, that might sound little okay. Anyway, weights in the sense parameters. Okay. So you want to keep your parameters in control. So again, there are two types of regularization. One is lasso and the other one is ridge. There are many others also, but let's only discuss these two as of now. Uh, in both of these cases, you add a term to the loss function. In the ridge case, you add lambda times norm of beta whole square. Okay. This is norm 2, by the way, Euclidean norm. And in lasso, you add the Manhattan distance or the L1 norm. So this is the L1 norm. This is the L2 norm. Okay. L1 norm is also known as Manhattan distance. This is the Euclidean distance. Okay. This is mostly about regularizers, and so the one more important thing I want to mention. This is actually a word of caution. Let me caution. Okay, so let us say I have some model. Okay, W equals beta 0 plus beta 1 x plus epsilon. Okay, linear, simple linear regression. So can you tell me what is the ridge loss? And let's say we have a data set D, xi comma I running from 1 to n. So the question is, what is the ridge loss, or the what is the ridge loss? So is it option A, summation I running from 1 to n yi minus beta naught minus beta 1 xi ka whole square plus lambda times beta 1 square, and option B is I running from 1 to n yi minus beta naught minus beta 1 xi whole square plus lambda times beta naught square plus beta 1 square. Can anyone tell me which of this is the correct ridge loss? Anyone? हेलो, सब भाग गए क्या? भाग गए सब लोग? नहीं, सब लोग. Can anyone tell me what
No,
is the
sir,
correct?
I haven't watched lectures, sir, so
Oh, I see. I see.
I don't.
B.
No, this
Option B.
option B. So someone says option B, but it is not correct. Correct answer is option E. Okay, so first of all, there is no need to watch. Okay, so I'll just explain it further. Maybe. So the ridge loss is where you add this guy to the loss function, right? Oh, so why I asked this question is because you don't apply the ridge loss to the bias parameter. In fact, any loss, any regularization, don't apply regularization to bias term. See, in our earlier discussions, in throughout all this, what was our crucial assumption? Our assumption was that this data set is centered, right? If it is not centered, we typically either you center it at then and then you do regression, in which case you can go by the previous notation. But if you are applying the bias term separately as b naught, then don't apply regularization to the bias term. I'll explain why. So the reason why I'm saying this is that, let's say you're applying okay, so let's say you have a data set which looks like this. Let's say it looks like this. Okay, this is my data set, right? This is my x, this is my y. Okay, now if you use, so typically what do we want? We want a line which goes like this, right? We want a line which goes like this. But if you use regularization on the, or penalty on the bias term, then you will end up getting a line like this. If you use regularization on the bias term, this is what we originally want. If you don't use regularization on the bias term, because if you use regularization on the bias term, this bias itself gets reduced, right? Because what does the regularization do? It doesn't allow these parameters to be very huge, right? But we want the bias to be as it is. We don't want the bias term to be regularized. Okay, that is the overall idea. What else? Any questions, guys? Come on, any questions? Not on what I have discussed now. In general, any questions?
Excuse me, sir.
Huh,
Sir, in the first term that you wrote, right, bias term plus the data, why we need to add the bias term? Because we, the equation of linear general equation of linear is y is equal to, slope into x plus some constant, right? So why we
some error,
have to
right?
add the, yeah, some error or, yeah, constant. So why we need to add the bias term?
Oh, I see. Okay, okay. So so you are saying, so what is the model, the linear model that you use? Can you tell me? Y equal to,
Wx or beta x plus some c or some noise.
okay, C and noise are different. Okay, so even if you're writing C, you have to add noise, and or you could just add epsilon. That is possible. I'll make a few distinctions here.
Mm-hmm.
One is y equals to I think x transpose beta plus epsilon. In this case, what is my y? Y is a, what is my x transpose, or what is my x? X is a matrix R D cross n. What is my beta? Beta is a vector in RD. Okay, and epsilon is a vector in Rn. And when I write this, I'm assuming that the data is centered. There are two things. Actually, there are two things. One is assume data is centered, because this assumption is, you can always do this, right? You can always do this. You can always center the data set, or you can add a series of ones to the x. So x is my uh, x1, x2, x3, and so on, xn. But in the first row, you have a lot of ones. This form you must have seen somewhere, and then uh, you have beta from beta 1 to d. So essentially, you have d minus 1 features, and the one extra feature is you want to capture the bias term, right? This is the case when you're adding the bias term. For, just give me a minute. Case we've actually added the bias term. Now, when you said y equal to beta x plus epsilon, can you tell me what is my y? Is it a scalar or is it a vector?
It's vector.
Okay,
Okay,
Rn,
Rn.
and beta is
It's also vector. Nardi.
okay. Beta
Okay,
is in
beta is
Rd.
Nardi.
So this, what is this x though? This is capital X, is it? Okay, fine. If you want to take it as small x, then also it is fine. So what is x? X is also in Rd, or is x a matrix?
Sir, if we taking the y in n dimension, then it will be the
Huh.
matrix X. And if
Exactly.
we
Yeah.
are taking individual y, then it will be the individual
Yes.
data point of, yeah, vector.
Correct.
It will be the
Correct.
vector.
So let me take y as individual r and x as Rd. Now let me ask you this question. So let us say d is 1, okay? And I have data points which are looking like this. What kind of line, if I fit y equal to mx, see epsilon is what? It is the noise. It is not the, so it's trying to capture the noise. It is not the model in itself. The model is just y equal to mx in your case, from what you have mentioned. And in that case, I will get a line always which is passing through the origin. But we don't hope our data to always to be centered around the origin, right? That is why we add the bias term. See, there are two ways to deal with this. Either you center the data set or you add the bias term. You can do anything. If you're adding the bias term, then don't apply regularization to the bias term. If you're not adding the bias term, then you can apply regularization. Then there is no bias term, so you can apply regularization to the entire uh, you know uh, parameters. So the
So
reason
the
why we
reason,
add the bias term is because uh, we expect our data set could be shifted from the origin, right? And to capture that, we add the bias term.
So
So,
means to make it centralized, we are adding bias term.
sort of,
sort of.
sort of.
Okay.
Okay. Because in this case, we want this red line, right? We don't want the green line. And this has a bias. This doesn't pass through the origin. This has some bias. What is the bias? This is the bias, right? Is it clear?
Yes, sir.
Okay, great. So yeah, so that is the takeaway, that if you're doing regularization, don't apply it on the bias term. I think even if you look at scikit-learn, it will tell you something similar. What else do we have? I hope you guys have read through this notion of overfitting and underfitting. It's pretty straightforward. Any doubts, guys? If there are no doubts, I'll wind up the session and I'll probably tell someone to add a session tomorrow for programming assignment.
Sir,
Any question,
can you
guys?
please explain overfitting once?
Sure, sure, sure. By the way, from what we derived, okay, from what we derived, can you? Okay, I'll explain overfitting first in simple language. Then we will discuss this. Actually, I'll share a post with you guys. Okay, which actually very extensively discusses how overfitting and bias variance is sort of related. Okay. Anyway, so let's say this is my x. Okay, and let's say I my data set looks like this. बारिश भी होने लगा यार. चलो. Okay, some sort of a. I'm just arbitrarily putting the data points, but I'm maintaining some shape. Okay, this is my y. Okay, so now let me draw three different curves. Okay, first curve is, let me use which color should I use? Black use करता हूँ. This is my first curve. Okay. Then I have another curve which looks like this. Okay, and then I have a different curve which looks like this. Okay, can you tell me which of these curves are better? Which one is better? Any guess?
So better in sense which curve tackles all the data points.
Ha, good question. So you're asking which what do I mean by better, right?
Is
It means that I want two things from the curve. One is that it should fit training data well. Training data is what you're seeing on this graph. Okay. It should fit training data well. Secondly, it should generalize well to unseen data. Okay. So this is essentially okay, leave it. Okay. So this is what I mean by better curve. Which curve is better?
so the black curve.
Yeah, the black curve. Okay. What is the problem with the red curve? Can you tell me?
So maybe it will not behave well for the unseen data.
Correct, correct, correct. So doesn't work well for unseen data. And what is the problem with the green curve? You can say that it doesn't capture all patterns of the data. In fact, if it doesn't capture the patterns in the data, then we say that the model is underfit. And if it captures too many noise in the data and doesn't work for unseen data, then we say that it is an overfit. Okay. So now let me go back to this guy. Okay. So overfitting is a scenario where this variance is high and the bias is low. Underfitting is a scenario where the bias is high and the variance is low. The other way around. You can see that, yeah, I think that is pretty much it. Any other doubts on overfitting? So, whoever asked, or is it clear, or should I explain more?
No, sir, it is crystal clear.
Okay, okay, cool, cool. Actually, if you don't stop me in between, then I will just go on saying this kind of stuff, and probably we will not our,
But sir,
what?
that's very helpful for understanding the basic understanding.
Okay, okay,
We
great,
don't
great.
mind.
Okay, cool, cool. I'll wind up the session now. Okay. Any other doubts or anything? Any confusions? anything like
Sir,
that.
what will be
Yes,
the
sir.
timing for the session, programming session tomorrow? Do you have any
Uh,
idea?
Let me think. How about afternoon, 3 to 5?
3 to 5, yeah.
Okay,
It's
tomorrow I'll ask Nikita to send an email or someone, or I will set up an email. Okay, I'll send a meeting link around. Either of these. Okay.
okay.
Okay, guys.
Thank you, sir.
Yep. Thanks. Thanks.